Hello. For our Capstone project, we are looking into underwater energy harvesting through piezoelectric materials. This project is sponsored by the Naval Underwater Warfare Center, otherwise known as NUWC. Overviewing our project's progress is our technical director, Reed Billings. The team consists of 2 electrical engineers. My name is Matthew Duke.
Hi, my name is Sean Doherty, and we are the NUWC Piezoelectric team.
For those of you that do not know, NUWC is the United States Navy's leading research, development, engineering, and fleet support center for all offensive and defensive weapon systems associated with undersea warfare, including submarines and autonomous underwater systems. They are located in Newport, Rhode Island, and employ more than 4,400 civilians and military personnel with a defense budget of over $1 billion. The motivation for our project comes from wanting to apply self-sustaining energy to unmanned underwater vehicles, otherwise known as UUVs. As you may already know, UUVs are mission-based systems. They carry instruments and sensors to monitor, inspect, and navigate underwater environments. However, the number one limiting factor of a UUV is its power capacity, keeping its missions limited in range and duration, often as little as 24 hours. Mission durations can be extended through the use of underwater power stations, but these have yet to be implemented commercially as they lack the practical power generation sources. Our project wants to make UUVs self-sustainable by applying the naturally occurring piezoelectric effect to generate power from the sound. Our anticipated best outcome of this project is to develop a piezo underwater sound energy harvesting model that will feature a resonator, piezoelectric material, AC to DC rectifier, DC to DC converter, and a microcapacitor. We would like to make a prototype to exhibit the capabilities of converting sound energy into power via piezo material. This will be intended to be tested and possibly support proof of concept.
Our team's key technical accomplishments up to this point include sound propagation and sonar research concerning thermocline and sound refraction in shallow water, sound energy harvesting through ambient noise and coming up with different resonator designs that cater to our underwater needs. Also, we looked into converting sound pressure into energy. Some more technical accomplishments our team made include piezoelectric research concerning that of the piezoelectric effect. These materials that we're going to be using, which are found in lead, zirconate, titanate, or PZT, to be the most favorable for our project given the large dielectric constants and mechanical factors. This material gives us a higher electrical output in response to the low resonant frequencies we need to output the most power possible. Moving on to the economic impact of the company. Our team believes that the idea of this project can bring attention towards alternative renewable energy resources that are available to us in today's world. In this case, our renewable energy source is underwater sound energy harvesting. Also, with the further development of this technology, there can be a crucial step towards self-dependability of UUVs in the future. Here's our system block diagram. We plan on harnessing the underwater noise using a resonator to amplify the frequencies that are provided from the sound waves and exhibit that amplified frequency onto the piezoelectric material. This will in turn convert those waves into AC energy. This is where we plan to implement a PCB, which will be able to convert that energy from AC to DC, then from DC to DC, and finally to our microcapacitor, which will then charge up and store energy until we can disperse it into a battery.
The topics of research I've been interested in this semester were resonator-based sound energy harvesters, the piezoelectric effect, and applications of piezoelectric energy. First, resonators are a must for this project because they can increase the resonance of a sound and in our case increase the power generated by the piezoelectric effect. The piezoelectric effect is of course when certain materials generate an electrical field in response to mechanical stress. In our case, the stress applied to the material will be amplified sound waves that can hopefully generate enough power to store a capacitor. But because this is an underwater application that won't be relying on any particular sound frequencies other than low frequency ambient noise coming from all directions, our piezo material needs to be of a certain composition that favors low mechanical factors. This is why we are considering a lead zirconate titanate based piezo, known as PZT, because of its large dielectric constants and lower mechanical factors. This means higher electrical output in response to lower resonant requirements, a perfect recipe for underwater sound energy harvesting. For my future contributions, I would like to acquire the following materials: the lead zirconate titanate piezo parts, a glass capsule open at one end that would work as our resonator, the electrical waterproof capsule, which will screw into the open end of the resonator, which I am also considering to 3D print, and of course the PCB design, which will include the AC-DC rectifier, DC-to-DC converter, and the capacitors. I would also like to contribute to a CAD design of the prototype so that we have an idea of what the dimensions will be. And lastly, the contributions to assembly and testing of the prototype. And now I will hand it back to Sean.
My technical contributions this semester consisted of research surrounding piezoelectric effect, sonar basics, UUV application, the power requirements of a UUV, sound propagation underwater, and thermocline. The piezoelectric effect is the effect created by piezo material when stress is applied to it. In our case, this stress is going to be created by sound waves that are going to be amplified through an underwater resonator. My research surrounding sonar basics was helpful to touch on things such as how sound propagates through water and thermoclines. A thermocline is the area underwater approximately 660 feet to 3,300 feet below the surface where the temperature gradually decreases, making the water more dense. This dense water greatly reduces the speed of sound underwater. A UUV requires around 200 to 500 watts of power for normal charging, and the docks that they are usually charged on require anywhere from 66 kilowatt hours and 2.2 megawatt hours per station, with rechargers taking approximately 4 to 8 hours. Some contributions that I plan for next semester include ordering the specific parts needed for the in-lab testing that we plan on doing to get a sense of how much power these devices output and how many we would need to be connected to a reasonable power output. Once these parts are ordered and tested, there is going to be a prototype design using a cantilever design inside of a resonator. This will hopefully amplify these underwater sound waves to a frequency that will vibrate the piezo material to a frequency close to its resonant frequency. Hopefully at the end of the semester, we are going to be able to deploy a prototype in the water. Some of the things that we would like to accomplish in the future is a CAD design with exact dimensions of the materials that we plan on ordering. We would also like to design a PCB for our prototype that will be responsible for the conversion from AC to DC, then DC to DC power, which will then be sent to a microcapacitor. After acquiring all materials needed for the prototype, we will then conduct lab experiments making sure it works the way we intended it to, and that it is waterproofed correctly. Deployment into a body of water is our final goal for the next semester, which will require the device to be positively buoyant and anchored to the sea bottom. Here are a couple things that we have considered to be risks when trying to reach the anticipated best outcome of the project. Our piezo material power output not being sufficient for application. We consider this a high risk. The lack of mechanical knowledge when it comes to the stresses applied to the piezoelectric material. We consider this one a medium risk. A team member has an emergency or a sickness that will hinder their contributions. This is a low risk. Here are some continued risks. One being our resonator not being able to amplify the sound energy significantly enough to trigger the piezo material vibration. We consider this one to be a high risk because we never know how this resonator is going to work with the piezoelectric material. And then lastly, for our risk, the inability to understand concepts in a timely manner that would hinder us in our prototype design process. This is considered a medium risk, I would say, seeing that we have been doing research for a whole semester and that we have a pretty good idea of what we need to do to get our anticipated best outcome. We'd like to thank our technical director, Reed Billings, for his openness towards our ideas for the project thus far and his continued guidance throughout the next semester. Thank you to Dr. Sunak for providing us with the opportunity to work with a company such as NUWC and to gain real-world experience based around our passions. Lastly, thank you to Mike Smith, Brennan Smerbeck, and Jack Murphy for their help and guidance throughout the Capstone program on risk management and project progression. Thank you for listening to our presentation, and we look forward to providing NUWC with the best anticipated outcome next semester. Thank you.